Hello friends. Welcome to T Academy. Let's continue the Tamil Nadu Teachers Recruitment Board exam triple paper solutions. Now we are solving the questions from the 51 here. Okay. So before going to discuss about these questions, previously I posted around 5 videos in this paper. So if you like the videos, please subscribe to my channel and share it with your friends. Okay. So let's continue here. A pair of roots has been moved further away from the imaginary axis, then the relative stability of the system will be. So here we are talking about the root locus, and roots are moved further away from the imaginary axis. So here we have a real axis and a j omega axis here. Now the roots are moved away from this imaginary axis. That means it is going towards the left side. Okay, and the stability of the system will be, the system is said to be relatively more stable or unstable. It is on the basis of settling time. Okay, so the system is stable or unstable, it depends upon the settling time here. Okay, if the settling time for the system is less, then the system is said to be stable here. Okay, the settling time of the root or pair of complex conjugate roots is inversely proportional to real part of the roots here. Okay, now so far, if in this question what they asked is the roots are far away from the imaginary axis. Okay, the roots are located nearer to the j omega axis. Okay, settling time will be large. Suppose if the roots are here, the settling time will be large here. As the roots move towards, as a move, as they move to move away from this j omega axis towards the left half of the S plane, settling time becomes more. Sorry, settling time becomes lesser here. So as the settling times become lesser and lesser here, what about the stability? It is going to be more stability, and stability will be improved here. So conclusion point in here is, as the poles are moving away from the j omega axis, okay, the relative stability will be improved here. Okay, next question here. The Nyquist plot of a first order system g of j omega is equal to 1 plus 1 by 1 plus j omega t here is. Now we will draw the polar plot for this transfer function g of s. So to do the polar plot, first we need to take the magnitude of this j omega and as well as phase angle. So first we will draw the table here. Now we will take the first of all magnitude here, magnitude, and second one will be phase angle here, phi will take. Now here we will take when the frequency is 0, when the frequency is infinity. For example, here we'll take, so magnitude means what I can say, magnitude m of g of j omega is equal to 1 by square root of 1 square plus omega square here. When we substitute this omega equal to 0, then it is equal to 1 divided by square root of 1 square plus 0 square when the magnitude omega equal to 0. Now what you can get here is nothing but 1 by square root of 1 means it's actually 1. So magnitude is going to be 1 when the frequency is 0. Similarly, when the magnitude is infinity, so we'll talk about magnitude when omega equal to infinity, then what you will get is 1 by square root of 1 square plus infinity square. So infinity added with 1 means it's nothing but infinity only. So 1 by infinity means it is equal to 0. So we got this magnitude plot. Sorry, 0 here. Next one. When we draw the phase angle, so g of j omega angle is equal to minus tan inversion. Why? Because 1 divided by, so minus tan inversion of omega by 1 we can take here. Okay, omega t by 1. Now when omega equal to 0, that implies Angle is how much? Minus tan inversion of 0 is nothing but 0 only. So we got the magnitude here 0. And similarly, when the g of j omega angle, when omega tends to omega is equal to infinity, we can say it's nothing but minus 90. So minus 90, it can be written as or we can write as a 270. So here we'll get it as minus 90 or we can write as a 270. Now check the options here. Which options is suitable here? When omega equal to 0, omega is 0, magnitude is 1, angle will be 0. So I'll choose option B here. See, real axis, when magnitude is 1 here, magnitude is 1, what about the phase angle? 0 here. And similarly, next case, here, when omega tends to infinity, magnitude will be 0. So magnitude is 1 here actually in the option in the problem. So it is going to be 0 here. Okay, so frequency is 0, frequency is infinity, we got it here. Magnitude 1 here and magnitude will be 0 here. Now it is touching the minus 90. So this is the plot here. Okay, so among the options, B is a right option for this question here. And the next question, 53rd question. Okay, select the wrong statement about Nyquist, so negative feedback closed loop system. I'll repeat the question. Select the wrong statement about negative feedback closed loop system. So what is wrong about the negative feedback? So negative feedback will have only one drawback, is it is a gain is going to be reduces. So except the gain reduces, it is having all the advantages. Okay, so it will provide the better stability, okay, and the low sensitive to parameter variations, okay, and rejects any disturbance signals, that's also is it, but increases the error. So this is a wrong statement. It is going to decrease the error signal. Okay, that is the reason we are studying this closed loop feedback system. Okay, though, so among these options, B is the wrong option. Okay, next question here, it is also from the control system. For the type 1 second order system, the value of maximum peak overshoot, actually here there will be they're asking about percentage maximum peak overshoot. Okay, now the answer is for this question e power minus, okay, uh, damping ratio into pi divided by square root of 1 minus eta square. Okay, so because of this printing some mistake error here, it's not visible, minus sign is not visible. So option A is a right option for this question here. Okay, next one, 55th question here. For the characteristic equation having more number of poles than zeros, the number of root locus branches will be equal to, okay, generally here whatever the poles or zeros, whatever the highest value, that will be equal to number of root locus branches here. So for example, in this case, what they mentioned is uh, more number of poles than zeros. So it indicates that poles are having a good number compared to zeros. That is more number in zeros. Okay, at this time, the root locus branches is equal to P only. Okay, why? Because the poles are greater than zeros. For example, in this question, they may ask it like this, reverse question. For the characteristic equation having more number of zeros, here right, zeros compared to so poles, then the number of root locus branches will be, so root locus branches at the time is equal to z. Why? Because number of zeros are more than that of poles here. Okay, so whichever the having higher value, that will be root locus branches here. So for the 55th question, the answer is number of poles when the poles is greater than zeros. Okay, if the same question is asked in reverse manner, that is number of zeros is having more number than compared to poles, means A will be the right option here. Okay, we'll move to the next page. Right. Now the 56th question, it is from the electrical machines, that is of transformers. Okay, so this formula which we already discussed in my previous videos of electrical machines, three-phase transformers, important points or important formulas. In that video we discussed this point. Okay, the advantage in a delta connection, if one transformer becomes disabled, the capacity will be reduced too. So when the three windings of the transformer are connected in a delta fashion here, okay, like this. Now one phase is disabled, so it is open circuited. Then the working part will be only two windings. Now when the healthy condition, it is supplying, for example, it is supplying 100 kVA. Now when because of this open circuited failure here, it is going to provide only 57.7 kVA rating only. But the advantage it will continue to provide its supply. So continuity of supply is required. So wherever you want continuity of supply, then we can use this delta connected transformers. So answer for this question is C here. Okay, so 57.74. Next question, 58 question here. In a DC motor, the mechanical output power actually comes from. So as the law of conservation of energy, energy cannot be created or destroyed. It can be transformed from one form to other form. And we know that it's a DC motor. So DC motor, what it will do is, it will convert the electrical energy into mechanical energy. It's the basic definition of a DC motor here. Now, where the energy comes from here, it is comes from the electrical input power only. Okay, so back EMF, air gap power and field system are the medium components from which energy conversion takes place. So the basic electrical energy input power is converted into mechanical energy. Okay, next question. This question is from the induction machines. Okay, now 58 question here. In a double revolving field theory of single phase induction motor, if the slip of forward motor is S, then the slip of the backward motor is. Okay, as we know that single phase induction motor is inherently a not self-starting motor. So single phase induction motor is a not self-starting motor. Okay, now in order to make this self-starting, we will provide some auxiliary winding and pony motor techniques are there. So with the help of the technique, we are going to start the motor. So to do that here, so forward slip is S and a backward slip is 2 minus S here. So answer is C is the right option for this question here. Okay, and the next question here. Capacitor start, capacitor run induction motor is basically. So just now I told you capacitor start, capacitor run motor is nothing which is used to start the induction motor. So induction motor inherently not self-starting motors. Okay, three-phase induction motor is a self-starting motor, but induction motor single phase means it is not going to self-starting. So we need to provide some extra accommodation here. Okay, that capacitor start and capacitor run. Okay, so capacitor start is going to provide the phase displacement between the main winding and auxiliary winding, and the capacitor run motor is used to improve the power factor of this motor here. Okay, so these two are different applications. Now, it is basically a two-phase motor. So why? Because if you take this single-phase induction motor here one winding is there. Okay, so here you have one capacitor, and there is a one more auxiliary switch is there. We have a winding along with the capacitor here like this. So here we have a rotor. Okay, so there are two capacitors which are used to capacitor starting purpose, and second one is for running purpose to measure the power factor here. So it is a two-phase motor. Next question here. Okay, question number 60. Synchronous impedance method of calculating the voltage regulation of an alternator is otherwise other no other is known as, that is a EMF method. Okay, answer is EMF method. Okay, it's also known as a synchronous impedance method or a same or EMF method. Okay, and next question, this is from the uh, analog electronics. Okay, the transfer function of a operational amplifier circuit shown in the figure is, so we need to find the transfer function. So transfer function generally we study in the control system that it is a Laplace transformation of output divided by Laplace transformation of input, or we can also say it as the ratio of E naught divided by EI here. So in this circuit diagram, okay, so transfer function is ratio of E naught by EI. To find the transfer function here, what we will do is we will split this entire network into two parts. So let me divide this network here into two parts here. Now let me assign a value here, a mid value, say EM here. Okay. Now if I divide this, it is first off is a inverting amplifier, stage 1, and I can say this one is inverting amplified, stage 2. Now what I will do here, it is I will split this E naught by EM as a one stage, E into EM by EI. Now E naught by EM we can calculate. So first stage, okay. So first stage EM by EI input side. It is nothing but we know the basic formula minus of R2 divided by R1. So you know the basic condition here. Similarly, in the second stage we can write as E naught by EM is equal to minus of R4 divided by R3. Now substitute here, what you can get here, it is, now substitute these two values in the transfer function equation. So transfer function is equal to minus of R2 by R1 into minus of R4 divided by R3. Now when minus minus, okay, you will get it as R2 R4 divided by, so R1 R3 here. So the answer here it is R2 R4 by R1 R3. So A is the right answer for this question. Okay, so that's it for this session, friends. Thank you.